Okay, first things first, these are not typos. These are actual serious cases of an integral and a differential equation. And we're going to solve them using a class of integrals called product integrals. And we're going to evaluate the product integrals using their development in correspondence to the classic Reimann integral. So let's just get started. And before we get started with the mathematics of it, I would like to thank all of you for being patient with me regarding uploading content, because I've been under the weather because of the flu. So yeah, today I feel much better, and I'm in the mood for delivering some really cool content again. So first up, we're going to develop the product integral, and for that, let's recall exactly what the Reimann integral means, or how is it defined. So the integral from a to b of some function f of x with respect to x is defined as the limit of the sum over I from 1 to n, from 1 to n, as n approaches infinity, of f of x sub I times delta x sub I. And in similar fashion, we can define the product integral as being the integral from a to b of f of x to the dx equal to, again, the limit, but this time not of a sum, of a product over I from 1 to n, again letting n approach infinity, of f of x sub I to the delta x sub I. Okay, this looks pretty awesome, but we're used to working with the classic Reimann integrals, so it would be pretty useful if we could find some relationship between the product integral and the classic Reimann integral. And for that, I'm going to invoke the properties of the natural logarithm. And here on the right-hand side, provided that this product is non-zero in the limit as n goes to infinity, provided that the product is non-zero, provided that this whole limit is non-zero, we can switch up the order of the limit and the natural logarithm operators. So we have the limit as n approaches infinity of the natural logarithm of this product from I equals 1 to n of f of x sub I to the delta x sub I. And once again, making use of the incredibly useful properties of the natural logarithm, we can write the log of a product as the sum of individual logarithms. So we're back to a sum case, the sum over I of the natural logarithm of f of x sub I to the delta x sub I. And once again, we're going to make use of the properties of the natural logarithm and transfer this down here to act as a coefficient, or just some multiple term. So we have this logarithm term being multiplied by delta x sub I. And now take a moment to study the structure of the right-hand side. On the left, you have the natural logarithm of this product integral, and on the right, you have this limit of a sum, and the upper limit of the sum is going to infinity, of a function. It's the natural logarithm of a function. So yeah, it's a function times delta x sub I. So this is the exact same structure as the classic Reimann integral. So this is the same structure. That means we have the classic Reimann integral from a to b of the natural logarithm of f of x with respect to x. And this is awesome. So you have a very nice relationship between the log of the product integral and the usual integral of the logarithm of this same function. Okay, nice. And if I exponentiate both sides, I can get rid of the logarithm. I can get rid of the logarithm on the left because it's the inverse of the exponential function, right? So this implies that the product integral from a to b of some function f of x equals e to the integral from a to b of the natural logarithm of that function with respect to x. So now that we've developed this pretty awesome relationship, we can proceed towards evaluating the integral that you saw in the start of the video. It's the integral from 0 to pi by 2 of, oh, terribly sorry, of sine of x to the dx. And this equals e to the integral from 0 to pi by 2 of the natural logarithm of sine x with respect to x. And we know that this is one of Euler's log trig integrals, and it evaluates out to pi by 2 times the natural logarithm of 1/2, which you can write in a pretty funky manner, again invoking the properties of the logarithm. So you have e to the natural logarithm of 1/2 to the pi by 2. So these two functions cancel out, being inverses, and you have 1/2 to the pi by 2, and we know that 1 to something is just 1, right? So this implies that the integral from 0 to pi by 2 of sine x to the dx equals 1 by the square root of 2 to the pi, which is a pretty nice result indeed. Okay, now it's time to solve that ridiculous looking differential equation. So we had e to the dy being equal to x to the dx. So integrating using the product integral we just developed, we have e to the integral of the natural logarithm of this function of y, which is just the constant e in this case, dy being equal to e to the integral of the natural logarithm of this function of x, which is just x here, and of course we're integrating with respect to x on this side. So because of the equality of the exponential functions on the left and right, this implies the equality of the arguments. So we have the integral of dy being equal to the integral of the natural log of x with respect to x. So this is pretty straightforward. On the left we have y being equal to, you can use integration by parts here to get the answer of x times the natural log of x minus x plus c. Okay, cool. So that was a pretty straightforward solution development. Anyway, it was nice trying something so different for today's video. And I hope you enjoyed it. Be sure to like and subscribe. Thank you. See you next time.